Next is a lesson on parallel circuits. A parallel is a circuit or a portion of a circuit that has more than one path to follow. So if you look here, you've got 1, 2, 3, 4 distinct paths in this little example. If you think about a typical school building, especially our own building here, there's more than one way to get between different points. If we are upstairs in my room and we want to go downstairs to the library, there's two very easy paths. One, you go the stairs directly by my door and then down in the media center, or you go all the way down the hallway through the science classrooms and down those stairs right into the media center. Two very different paths, both will get us there. That's an example of a parallel. Now, equivalent resistance in a parallel can be found by adding the reciprocal of the resistances. Look below. If we have a 2 ohm resistor, a 5 ohm resistor, and a 4 ohm resistor, to find the equivalent resistance, we follow this formula. 1 over the equivalent is equal to 1 over R plus 1 over R plus 1 over R. Let's throw in our numbers here. And we see 1 over the equivalent resistance is equal to 1 over 2 ohms plus 1 over 5 ohms plus 1 over 4 ohms. This right here may be the trickiest thing. If we just add up these fractions, we're not done. We still have to take the reciprocal to get the answer. Because if you just add these up, you have whatever you get is equal to 1 over R. Now you could add it in terms of fraction, make this into 20ths, and come up with 19/20ths. Or you can convert it to fractions, or to decimals rather, which is my preferred method here with these. So I'm going to say 1.5, 0.2, and 0.25. And when I add those up, I get 0.95 over an ohm. And that reminds me, when I write it that way, it reminds me that 1 over R equals this over the ohm. I have to cross multiply or I have to take the reciprocal. Either way, my answer is not 0.95. My answer is, when I'm done doing that little bit of math, 1.05 ohms. This is my answer, 1.05 ohms. Notice, that is a lot less resistance than each individual path, and that's a cool thing about parallel. The more you add paths, the less the resistance is. So, potential difference in a parallel is the same across each possible path. So if we have a total voltage of 9 volts, each path has 9 volts available to it. 9 volts available. So that's kind of neat. So our rule here is total voltage is equal to the voltage along each path. Now let's compare current to students in the hallway. Must they all take the same path? The answer is no. There are 3 distinctly different paths that they can follow. So the total current is now split amongst the paths, proportional to the resistance. We're going to end up with more current here along the 2 ohm path than we will along the 5 ohm path because that's the most resistance. To calculate these currents, we would have to take and say I equals V over R, so 9 over 2. 9 over 2, 9 halves. That's like 4.5. Okay, so let me write. This would seem to be 4.5 amps. And 9 over 5, that's 1.8 amps. And 9 over 4 is 2.25 amps. And if we want to compare, that there is going to add up to, what does that come up? My calculator says to me when I add those 3 things up, I get 8.55. 8.55 amps is what my total is when I add those up. Or we can cross-check and say I equals V over R and use the equivalent resistance. So 9 volts divided by 1.05 ohms. I'm sorry about my messy writing. I'm using the mouse from the computer desk. And that comes on my calculator to be 8.57 amps. This difference comes from rounding here. Okay, that's where that difference comes from, is rounding on getting that equivalent resistance. But as you can see, that's pretty darn close. So there's our current. The current is split amongst the paths. Clearly, the less resistance path got more current. The heaviest resistance path had the least current. Let's recap our rules. Equivalent resistance, you add up the reciprocals of each resistance. Voltage is equal across the paths, and current is added up across the paths. A couple ideas about parallel circuits. If I remove one resistor, the remaining resistors keep working. If I add more resistors, each resistor keeps working at its original level. So that's kind of neat if you're thinking about electrical wiring. By adding more resistors in a parallel, you're not decreasing the overall power to everything. That's kind of neat. Let's look at this sample here. We need to find the equivalent resistance here and find the total current. So let's pause the recording and let you work through that. Find the equivalent resistance and then find the total current. Go. At this point, I'm ready to proceed, but if you guys are still working, make sure you have it paused. All right, here we go. If we take our things and we say 1 over 2 ohms plus 1 over 4 ohms plus 1 over 5 ohms plus 1 over 7 ohms. What I did here was I wrote those in their decimal forms. So 1 over 2 plus 1 over 4 plus 1 over 5 plus 1 over 7. Put them in their decimal forms. When I add that up, I get 1.09 ohms. 1.09 over ohms. So that's equal to 1 over the equivalent resistance. So we're not done. That's not our final answer. So the last thing you need to do is take the reciprocal of 1.09. So 1 divided by 1.09, and you get an answer of 0.917 ohms. That's the equivalent resistance. Notice from the previous example we did in the notes, the resistance got even smaller because we added a 7 ohm resistor to it. It just keeps decreasing our overall resistance. Then to find total current, we take our 9 volts divided by our 0.97 ohms, and you'll end up with a current of 9.8 amps. So there you go. What we would follow up now with is some homework. Homework, page 643, 1 through 4.